So hello everyone. My name is Mert Koşan. I'm a PhD candidate in University of California, Santa Barbara in Computer Science Department. So today I will present our work, Global Counterfactual Explainer for Graph Neural Networks. And this work is done in collaboration with Zishi Huang, Sora Media, Sayan Ren, and Nambu Singh. So deep learning achieves the best performances in various application domains, and understanding deep learning decisions is a critical problem, especially in high-stake application sectors such as healthcare, law enforcement, or finance. There are multiple recent articles discussing that explainability and transparency should be the main core of your application, AI application. This will build trust between human and AI, and the ethical problem using AI systems will not be an issue. And another article from Nature claims that some scientists are already using chatbots such as ChatGPT as their research assistants. However, the quality and correctness of these chatbots are questionable. Therefore, we need to explain these deep black box models. So, our goal of this work is to present a postdoc explainer for those deep black box models. Okay, thank you. And here we have an AI decision system which classifies a mortgage application, and this particular application is denied by the system. Now we need to understand the reason. So one way is to check which features are actually relevant to this prediction. And here, for example, depth parameter can be important, so the customer should focus on. Better way of explanation is to provide recourse in terms of a counterfactual. And counterfactual is another instance from the opposite class, ideally with minimal changes. For example, here, if we change depth parameter from medium to low, the application will be approved. On the other hand, another way is a global counterfactual will define a general rule, and which makes it easier to explain compared to local counterfactual one. For example, here, if the rule is the credit score, if the credit score is medium and the stable job year is 2, then the depth should be less than or equal to low to get approved. As in graph explanations, the idea is similar. So here we have a graph neural network decides a formaldehyde molecule is mutagenic molecule. In our context, it's an undesired molecule. Now we need to understand the reason similarly. So one way is similar to feature importance. We can check the subgraph, which subgraph is relevant to the prediction. And here, for example, the carbon-hydrogen bond is the reason. Similarly, in the mortgage application, we can also have a local counterfactual of formaldehyde. If we remove the hydrogen bond and add hydroxyl bond, we will have a formic acid, which is non-mutagenic molecule. However, subgraph importance and local counterfactuals are unlike to show the bigger picture. Local counterfactual methods will, again, similarly, previous slides, it will define a general rule which makes it easier to explain. For instance, instead of providing formic acid as a counterfactual example to formaldehyde, we can say, given any molecule with carbonyl group, it needs to have hydroxyl bond to be non-mutagenic. And our work, this paper is the first one exploring global counterfactuals in graph domain. So our goal is to find global recourse R such that globally and counterfactually explain the prediction made by GNNs. Specifically for any undesired graph G, R of G should be desired. In binary classification context, if we let class 0 equals to undesired class, if GNN of G is 0, GNN of R of G should be 1. We want to make our model not complex because we want to have an explainable and simple model. And to satisfy these two conditions, we let our global recourse R as counterfactual summary graph set C. and all the graphs in that set will be desired. With this way, our R will be recurse rule, because you can, given any undesired graph, you can find a counterfactual as a closest graph from our summary set. And we can use some distance metrics such as graph edit distance. For example, here we have a two counterfactual C1 and C2 and one undesired graph G1, and the distance are 5 and 10. So the counterfactual of G1 will be selected as C1 since it is closer. And this way will make our R is easy to explain. Now we define C, but how do we quantify the quality of C? So one criterion is cost, where we are trying to minimize the recourse cost for all undesired graphs. And cost is important because we want to aim to find the most similar graphs as counterfactuals to all undesired graphs. So for instance, here, when we have two counterfactual graphs, since we are selecting the closest counterfactual, C1 will match to G1 and C2 will match to G2 and G3. And we can have the summation of each path 5 plus 3 plus 15 as the cost. Second criterion is coverage. So we will have a given edit budget theta. It will be impossible to cover all undesired graphs. And our aim is to maximize the coverage for representing all undesired graph by our summary set. In the same example, and our edit budget theta equals to 5, G1 and G2 will have a potential candidate in the set, so they will be covered. However, G3 will not be covered because it's far away from the counterfactuals in the set. So the coverage value will be 2 by 3. The third and the last criterion is interpretability. Our aim is to make this set C is as small as possible to make it easily analyzed. So based on these criteria, we formulate our problem as maximizing coverage of set C such that size of C will be given budget K. And in the paper, we show that this problem is NP-hard, and by reducing from maximum coverage problem. Now, I will introduce our heuristic method to solve this NP-hard problem. So to generate counterfactual summary set C, first we need to generate counterfactual candidate S. And efficiently explore the search space, we leverage graph edit map, which represent as neighbor graphs with one edit. And edit can be not edge removal in the original input graph, nor not edge addition or node label change. With this way, we will find the most similar graphs as counterfactual to undesired graphs. And to efficiently search the space, we propose to use vertex reinforced random walk, which considers number of visited information and importance of each visited graph. And in the literature, it has been shown that vertex reinforced random walk converges to representative set based on the importance function. And this is useful for us because we also want small representative counterfactuals that covers all undesired graphs. So importance function here is critical and problem specific. So we use GNN probability to only explore the counterfactual graphs. We also use coverage and gain, which represent how many additional undesired graphs will be covered by this new candidate. Since we cannot explore all undesired graphs, all graphs in the universe, we start with a random undesired graph in our data sets. We explore the neighborhood and some probability going back to another undesired graph. With this way, we will explore the neighborhoods of all undesired graphs will end up having representative counterfactuals. After we have counterfactuals candidate set S, we apply a simple greedy algorithm to find size K subset of them as our final counterfactual summary set C. In our experiment, we use 4 well-known graph classification datasets. And since we are the first global counterfactual explainer, we compare our methods with 2 local counterfactual state-of-the-art explainers and ground truth counterfactual, which are actually the graphs from the opposite class in the same dataset. And this table shows coverage and cost performance with size of C equals to 10. And our method outperforms the baselines in all metrics and datasets. The below figures shows coverage and cost performance with different size of C from 1 to 100. And our method consistently outperforms the baselines in under different size. To show the usefulness of our methods, we also conduct a case study. So here we have 4 undesired input graph from the AIDS dataset, which are inactive against AIDS. So the counterfactual of these molecules will be active against AIDS. And we generate local counterfactuals using our baselines. And they actually remove 1 or 2 edges from the original molecules, which makes it hard to generalize. However, our methods generate global counterfactuals, which actually defines high-level recourse rule. And indeed, while the input graphs have ketone or ether structure, our method managed to change to aldehyde structure. And in the literature, it has been shown that the molecules with aldehyde structure are actually useful combating HIV. This also demonstrates the usefulness of our methods in real-world graph application, such as drug discovery. As a summary of our contributions, we formulate a new problem of global counterfactual reasoning of GNNs in graph classification. We show that the problem is NP-hard, and we present the first global counterfactual explainer in graph domain. We also show the effectiveness and usefulness of our methods via experiments. And we hope our work can help researchers in exploration of explaining graph models and deep learning. Thanks.
Hi, just a question. In the different runs of the method, how much is the variation of the results? Is always the same deterministic or the standard variation, more or less? Yes. For the metrics, say the results varied between the different runs of the method. How much? So the stability of the method, more or less. Yes.
So the baselines, actually, they are not finding meaningful counterfactuals. They are actually finding a forest. As you can see in the example, they remove a edge between oxygen and carbon, which makes it forest. And they don't consider the difference between one of the biggest difference between local counterfactuals and global counterfactuals, the coverage. They don't consider coverage, so they only cover the one graph, the one instance. So, and they don't consider the cost. So they basically, all the local counterfactual methods try to find an instance that's actually GNN gives a similar prediction. And they actually optimize in a way that the factual will give you the same prediction, and they remove the factual part from the original graph to make it counterfactual. That's the way how perform.